कार्यक्रम की शुरुआत करना चाहूँगी हमारे माननीय निदेशक महोदय को आमंत्रित करते हुए कि वे कृपया स्वागत भाषण प्रस्तुत करें।
Very good morning. It is my absolute pleasure to welcome all of you today to this very special event, something that we at NCL have been wanting to start, at least I have been wanting to start it ever since I came back in April 21. It's in the memory of one of our fondest members of NCL, Dr. B.D. Kulkarni, or BD as all of us used to call him. It was one of the saddest days when few years ago he was no longer with us, and we all have very, very fond memories of BD. One of the finest gentlemen that I have come across, and one of the sharpest brains, and one of the most intelligent chemical engineers that I have had the privilege to work with. I have many at a personal level very fond recollections of interacting with BD, and I can spend an hour just talking about them, but I'll tell you a couple of them which to me embodies what BDK stood for. It was the first day when I joined NCL, and Dr. Mashelkar was the director, and he asked me to go around and meet a few people, and one of the first one who I met was BDK, and I had a 20 minutes meeting with him, and it went on for, I don't know, 2 hours 20 minutes or something like that. He asked me about my work, my PhD, because I just joined NCL. It was my very first day in NCL. I still remember April 8, 1993. And I went and met him, and we started talking about he asked me what I was doing, what I did in my PhD, and we started talking about it. And immediately he was able to grasp the essence of what I was doing. He captured it in a couple of lines, and then we discussed a lot in details about all of that. But that first few minutes itself gave me the impression of the sharpness of his brain, the ability to get right to the, to tear away all the other stuff which is not important and go right down to what is the most important part. And he didn't know anything about my PhD work, and he was able to grasp it within no time. And it really impressed me. And I knew at that time that I had come and joined the right institution. If we had people like BDK in this organization, I immediately thought that this is the kind of place that I always wanted to join. It was about 2-3 years later when we had started, a small group of us started a complex fluids symposium. For the first time we organized it in ISC Bangalore, and it has now become a huge annual event, but that was the first year. It was 1995, I think, or 96, and we had invited BD to give the plenary talk in that. And he was to come late, so he was not the first speaker. Normally the plenaries are the first speakers, but we arranged his talk at the end of the first day. And all of us gave our talks with, in those days, PET slides, transparencies, we gave our talks. And at the end of the day, he stood up to talk, and he didn't have a single transparency with him. He just spoke extempore. And the fluency with which he spoke, the articulation of what he was doing that he's talked about was just so mind-boggling. It was just incredible. And he always worked in those rarefied, realms of chemical engineering. He was so early in everything that he did. I don't think there were very many chemical engineers at that time who were talking about stochastic reaction engineering, non-linear dynamics, and most importantly, data mining. So I remember his talk in complex fluids. He was talking about high-dimensional planes of how you use them and those theories to look at non-linear dynamics of complex chemical reactions. You could understand him for about 5 minutes, and then he went into a hyperplane that only a few people could understand. That was the complexity that he was dealing with, and that was the sharpness of his mind that he had. The biggest loss that we have beyond BDK as a human being at NCL was that now what is machine learning and artificial intelligence based on neural networks and so on, BDK was doing this in 1980s and in the 90s, and he was already there, and he was applying all these data mining, data analytic techniques 30 years ago in the realm of chemical engineering. And we thought he was doing very esoteric work, and we didn't understand what would be the use of something like that in chemical engineering, right? And we didn't, at least I wasn't sharp enough to grasp the importance of what he was doing and how it can be applied. But today, look at it. No, everybody talks about AI and ML, and we don't understand much of it. I don't understand a lot of neural networks, but I still talk about it because everybody talks about it, right? But he was one of those very few people who probably laid the foundations insofar as the use of those tools are concerned for chemical engineering. We have unfortunately not had the foresight and the vision to continue that group at NCL. With BDK and his small group of people, I'm so happy to see many of you here today. When they left NCL, we have basically lost that expertise, and lost it at a time when it was the most important. I think as an organization, this is a big experience, a learning experience for us to be, we should not make these mistakes again. We should have that ability to look in the future and see what is going to be important, and it may sound esoteric today, but it's going to be one of the most important things in the future. We should have that ability to learn that, understand it, and make sure that we don't lose out such expertise in the future. So that was BD. He was a very, very fine gentleman. The third thing I wanted to tell you was a personal incidents where I was very low. I was feeling very low, and I something happened that sort of was pushing me to exit NCL, and the only person I thought I should go and talk to right away was BDK. And I went to his room, and as usual he was sitting staring outside the window. I'm sure you have seen him, right? He was sitting there staring outside the window, thinking about things probably that we could not even contemplate. And many times when I saw him, I would not go in his room because I didn't want to disturb that chain of thought that probably was happening in his mind. But that day, I felt like disturbing him, and I went in and spoke to him. And his gentle mentoring, his softness, his ability to take all that pain from you was so incredible. So he was really and truly a real mentor, a very, very fine gentleman, and I miss him a lot. I'm sure many of you miss him a lot. So I wanted to start this lecture series. This is the first one. It will be an annual event, and I'm appealing to many of the colleagues of BDK to help us have this lecture series as a continuing one. We fund this through the Research Foundation, but we are also looking for support from all of you. We have a runway to take this lecture series for 2-3 years, but we will need your support to make sure that it happens on a year-on-year basis. With that, to start this first lecture series, the first lecture, when Dr. Shivaram wrote to me that Professor Ramani Narayan will be coming to Pune, and would you mind hosting him at NCL, I grabbed this opportunity because BD was the leader for the lactic acid program, one of the largest technology development programs that we were doing at NCL, and Ramani is the world authority on polylactic acid. So I thought this would be the most appropriate time to get this lecture series off the ground. So Thank you, Ramani, for accepting our invite, and thank you so much for delivering this lecture in the honor of a person that we all admire and respect very, very immensely. Thank you so much.
धन्यवाद डॉक्टर आशीष लेले। आपने डॉक्टर बी.डी. कुलकर्णी से जुड़ी हुई अनमोल स्मृतियाँ साझा की और इस हॉल में बैठा हुआ प्रत्येक व्यक्ति समझ सकता है कि आपकी उनसे कहीं ना कहीं पर्सनल बॉन्डिंग भी थी। तो देखा जाए तो वे एक महान वैज्ञानिक तो थे ही, महान व्यक्ति भी थे, और ये व्यक्ति भी ना कह के हम उन्हें संस्था कह सकते हैं। तो कई संस्थाओं के बराबर उन्होंने कार्य किया है और हम सब बहुत सौभाग्यशाली हैं कि हमें उनके साथ उनका आशीर्वाद पाने का मौका मिला है। तो उनकी अनमोल स्मृतियों को प्रणाम करते हैं और बढ़ते हैं कार्यक्रम के अगले चरण में। मैं माननीय डॉक्टर एस शिवराम जी को सादर आमंत्रित करती हूँ कि कृपया वे मुख्य अतिथि का परिचय हमें प्रदान करें।
Why don't you all come inside and sit down? Close the door. Please close the door. Come inside and sit down. Please sit down. There are enough seats. Very good morning. Ashish, Sarika, thanks for giving me this podium for a few minutes. It's an honor and a privilege. Honor because you asked me to speak on the first memorial lecture in honor of BDK. I think each one of us had different facets of association with BDK, but for me, he was my good friend. I see Ravi Kumar sitting here. He was my good friend, a valued comrade in arms for 8 years. For 8 years, my burden was absolutely reduced as a director because he was my deputy director. And I knew that I had a shoulder on whom I can implicitly rely upon, and I would not get anything except the best advice. And that was, I think, one of the remarkable partnership two of us had for 8 long years. He was an erudite scholar, which I think Ashish mentioned. I don't want to talk more about his scholarship. I'm not even competent to do so, but I think he was the tallest scholar, not only in chemical engineering, but in every subject that he touched in his life. His scholarship was unexceptionable. He was also a go-to man. In fact, I wish every institution, every lab has some persons like this to whom we can just go and open our hearts without being judged. And I think every organization should have people like this. We must actually grow people like this because we need this. You can't go to the director every time, because the director is somehow in a chair in which he is judgmental, okay? And that therefore people don't trust that chair. Okay, so you need a second person in the organization who is equally tall in stature, and people know that he has the ears of the director. Okay, and therefore if you go to him, somehow the message will reach the director. And that second tier, what I call the shoulder for people to take their feelings and their frustrations, their aspirations, whatever they feel, they need somebody to talk to, And I think this is a person, and that for that person, that quality, he must be a great listener, He cannot talk, okay? And he must be a very deep listener. And those of you who have met B.D. Kulkarni, I don't know how many of you are in this audience who have ever met him. When you talk to him, he closes his eyes. I don't know how many of you have noticed it, He will close his eyes because science tells us that your faculties of listening works best when your eyes are shut, okay? Because if your eyes are open, your mind is wandering. And the only way to focus is when your eyes are shut. No wonder when you meditate, you shut your eyes. When you listen to good music, you shut your eyes, because that's the only way your oral quality will improve. And I think BD understood that piece of science, and therefore every time you speak to him, he will shut his eyes. And those people who do not know him may think he's gone to sleep, but he is not. He is listening, okay? He is listening, and he wouldn't say anything at all. And I think that quality we find in very few people. That quality is not in me. I tend to talk too much, listen less. But therefore, I had a great man like BD who could talk less and listen more, and therefore together we could balance this process in the office that I held for 8 long years. And I miss him deeply, because he was, as I said, I could just walk into his office any time with any problem that I had in administration, in managing people, in technology, in science, and ask him, what does he think? And I knew that whatever he said would be absolutely right, and that confidence I had. And therefore sometimes I would have made up my mind, I'm just looking for that revalidation of my thinking. And but then if he tells me something that I had not thought about, then it's time for me to go back and think again. And I think this was a great partnership that I had. As I said, he talked very less. Even in meetings, I don't know how many of you have seen, he will talk very little, and he will close his eyes all the time to listen. And I think that was one of the remarkable qualities. But when he uttered a few words, believe me, every word was worth its weight in gold. And I hope that many of us, including me, can even now learn that capacity to listen, because people say that the one quality that humans need most in this noisy world in which we live in today is the power to listen, and I hope that BD gave us that living example, and I hope that we will remember him for all times to come, and I hope NCL will remember him for all times to come, because it's not very often that we see people like BD amongst us. Thank you, Ashish, for creating this memorial lecture. I think we should honor every one of our legendary leaders of this institution. We are here because of them, and if there's anything I can do to contribute, please let me know, and I'll be very happy to ensure that this event not only is supported vigorously, but you have the best of the people in the world come and speak to us on this occasion. Having said this, it's also a privilege today for me to kind of introduce Ramani. I don't know why Sarika asked me to do so, but as I said, I like to speak, okay? So, and Ramani also likes to speak. So we share this, quality, because both of us like to speak, whether we are right or wrong, okay? And so Ramani, I don't know how to introduce him. I think you have, circulated a lot of minute details about him. I think all those things are nice, but I think he goes beyond those written words. I've known him for almost now 20 years, 22 years. He came to NCL, and it was amazing that in those days, we never used to call biodegradable polymers. So there was a term which was politically right, and he knows that, because there were lots of, what is called arguments in the world, what is the right word that we should use. And there were some powerful European scientists, and he knows who they are, who said, no, we should call these things environmentally degradable polymers, okay, and not biodegradable polymers. Now, so in fact, we had a number of meetings I and Ramani attended, not only in NCL, but in different other parts of the world. The venues were beautiful, but I don't think any conclusion was reached whether, something in which you put in a little bit of a cerium stearate and make it oxo-degradable is an environmentally degradable material, or whether something like polylactic acid is environmentally degradable material, or a polyethylene made from ethanol is environmentally degradable material. You know, now all these questions were unanswered, and I think they are still unanswered today. You know, so that's what yesterday we were talking. So 25 years on, we are still asking the same questions and trying to struggle to find the same answers. But in this cacophony of noises that abounds in this world, I think Ramani has had a singular voice, and this voice has been consistent, and that's what I like about him. He has not changed his stand depending upon where the wind blows, because these are very complex topics, and these topics are so complex because there are environmental lobbies, there are industrial lobbies, there are scientific lobbies. You know, I mean, all lobbies are exceedingly strong lobbies. You know, and so therefore you have to fight these lobbies at the same time. Be frank enough to say the truth and not become unpopular, you know, and it's not easy, you know, because you know, being a professor, you know, you can become very unpopular, you know, if you say all the wrong things to the wrong people, you know, or the right people. Anyway, so but Ramani's qualification, apart from all the other things that you have written about him, is that clarity of thought that he has had, and consistent clarity of thought that he had, and which I have seen it now for the last 20 odd years. And he has been saying the same thing, except that he has more and more data to substantiate his arguments compared to what he had in 1998. And therefore, I think he has come a long way, and therefore he is today the most respected voice in this discipline, you know, and that I can tell you without any if Ramani speaks, people listen, you know, they try to figure out, is there a truth in what he's saying. We don't have a solution to any of the problem as yet, and I'm sure Ramani can exemplify that. We don't have a silver bullet as yet that will resolve all these problems that we are facing today in terms of packaging of plastics. But I think he is giving us a sanity of thought, a way to think which is sane. And I have a feeling that just like in any aspect of sustainability, plastics, the first thing is to have a sanity of thought, and then of course solutions will evolve and follow. But let's not jump into solutions by simplifying or oversimplifying the problems, you know. And I think I have learned this in my 20 years of constant discussions in various forums, in various, you know, hotels and conferences around the world with Ramani, and I have been a great beneficiary of this. He by the way, he trained himself in India. He's a PhD from Bombay University. It's amazing that he was trained as a chemist, and now he is bordering on chemistry and chemical engineering. His first postdoc was in the laboratory for renewable resources engineering at Purdue. In fact, in 1989, there was a news item from Purdue, and that was the first time I heard about him. You know, now since I was a Purdue alumnus, I was on the alumni newsletter, and in 1989 there was a alumni newsletter started about somebody called Ramani Narayan coming up with some starch-based blends in plastics. Okay, and that was in '89, and that was something that in those days, you know, internet was not there. We used to get this you know, printed alumni newsletter, you know, by post. Okay, and I got one of those alumni newsletters from Purdue. In that I saw Ramani Narayan's name, and I said, who is this Indian doing something like this in Purdue? And I went back and started looking at a little bit of, you know, his background and his publication, and that's how I really touched base with him, purely by an information flow from Purdue. He has, of course, authored enormous amount of very significant papers. In fact, some of them he is cited in his abstract, but those of you who want to, in fact, he wrote the first definitive paper in 2015, which I think is now close to 10,000 citations with Jambak on how plastics move from land to oceans, you know. Now, this was, I mean, people had suspected that mismanaged plastics waste moved from land to oceans, but this was still not something that people really understood the processes by which this was happening. And they wrote a very seminal paper in Science in 2015, which I hope many of you must have read it. And that paper really taught us how do plastics migrate from land to water, you know. And this is a seminal paper in 2015, which I believe it is now close to 10,000 citations. The reason is because that was the time when that kicked off this entire discussion about the mismanaged part of the plastics waste. You know, the managed part of the plastics waste is we keep on focusing on, you know, and I think what we need to focus is not on the managed part. The managed part, there are technology solution, but what about the mismanaged part? What are we doing about it? And I think that is the preeminent question that scientists must ask. Let's not talk about recycling, let's not talk about this, let's not talk about that. Those are all managed part, okay? Now, in spite of all that great management, 20% of the plastic will still leak into the oceans, okay? Now, what are we going to do about that is a question that I think is the more fundamental problem that scientists must address. Too much of attention is being focused on recycling and you know, other things. Those are all managed part, or advanced recycling or upcycling, chemical recycling. These are all part of the managed part. This is not going to solve the problem of what I call the mismanaged part. And the mismanaged part is, I think, is what is drawing far less attention today. So maybe Ramani can throw some light on it. Thank you very much, Ramani, for coming here and spending some time with us.
धन्यवाद डॉक्टर शिवराम जी, आपने बहुत ही अच्छे से हमारे प्रमुख अतिथि का परिचय प्रदान किया और माननीय डॉक्टर बीडी कुलकर्णी के बारे में भी अनमोल स्मृतियाँ और आपकी जो बॉन्डिंग थी वो शेयर की। और निश्चित रूप से जो आपने कहा कि ऐसे व्यक्ति हर संस्था में होने चाहिए, बिल्कुल सही बात है। और आपकी इतने वर्षों की उनके साथ पार्टनरशिप रही है और आपने बहुत सारे अपने अनुभव भी हमसे बांटे। निश्चित रूप से आपने बहुत से उतार चढ़ाव साथ में देखे होंगे और आपको सुनना अपने आप में एक बहुत बड़ा ब्लेसिंग है, बहुत बड़ा सौभाग्य है। बहुत बहुत धन्यवाद सर। और इसी क्रम में आगे बढ़ते हुए आज के व्याख्यान के लिए सादर आमंत्रित करती हूँ आदरणीय प्रोफेसर रामानी नारायण जी को।
Yeah, I'm going to talk from there. So, but I'll use this. I think it's on, right? Yeah. The light is not on. Okay. I like it. They turn the lights off, people go to sleep. I never let my students sit in any class with lights turned off. But no, that's fine. I'm okay with that. Well, thank you thank you Shivram and thank you Ashish for inviting me. I'm particularly honored that you invited me for this lecture honoring BDK. I did know him, although as Shivram pointed out, he didn't talk too much, so I never knew whether he appreciated what I said or he was last in it. But because he worked on lactic acid, which was my pet subject at that time, I thought that that was very nice of him, and he's very warm-hearted, and you know, I'd meet a lot of people, but when Ashish said, "Oh, will you be willing to speak?" and by the way, we are doing this BDK lecture series, I just couldn't resist. I had to come because he was truly a gentleman, and there are very few people like that. I mean, very soft, very quiet. So I am delighted to be here. I wish I'd known him more, but thank you, Ashish, for inviting me to speak on this, and thank you, Shivram. You give half my lecture, I'm not sure what I should speak then now. we sort of mind melt, and he tells all the things I'm supposed to say. But thank you, Shivram, for inviting me also. And I thought this would be a very different kind of lecture. If you are looking for NMRs and looking for very deep thought process, this will be deep because this is going to challenge you. Okay, so let's begin. I'm going to talk about this term which we use a lot: bio-based, biodegradable, compostable. These words is thrown a lot. And I was telling Ashish this morning that I used to get very upset. It was exactly 25 years old. Shivram was the director. I think, no, you were in the organic chemistry. Mashelkar was the director at the time. We had this beautiful lunch. And I was arguing with all the OXO people, how can you say things like that? Actually, it was even more profane. I said, how can you say such stupid things like that? Now I've become more wiser. I lost my hair. I'm more milder and I'm more gentler and kinder in what I say, right? So I learned it. But it has not changed. It's very true. But it has become more efficient the way we say it. And hopefully we will settle it. And my gripe has always been, which is what I was expressing to Ashish too, is this is a powerful group which has got scientists and engineers. And I always wonder why you don't speak out, Why is it that a guy who says that I have this magic dust and it will biodegrade, or I have this mealworm which is going to eat all the plastics in the world and take care of your problems, you guys just smile and say he's crazy, let him go and say whatever he wants. And then the newspapers pick it up, publish it, and then everybody says, oh, all we need to do is grow a set of mealworms and we'll take care of our plastics problem. And you know that's not true. That's easy to go. So my goal in all of this has been to collect data and information to present to you as to how to articulate and communicate why some of these things make no sense and what you should do, right? So let's begin. And when I put this slide, I was a little afraid. I said, what am I telling you guys? What is plastics? But what I wanted to point out to you is everybody focuses on the back end of it. It's a long molecule, it is this, it's that. But I want you to focus on the first part of it, carbon. So these are carbon-containing molecules. And carbon management is the problem today. Or not a problem, it's an issue today. And that's what I want to talk about, carbon management through end of life. Right? So let's start with this term, bioplastics. I mean, you have heard this a lot. Every time I go, this is a bioplastics industry, everybody is into bioplastics. Did you know that the word bioplastics has no meaning whatsoever? What is bioplastics? Can you tell what is bioplastics? Can you define it like you define a polymer? The answer is no. It's a nice word, so we picked it up, and it is like a coat rack where you go to hang it. So bioplastics by itself has no real meaning. It simply has the word bio in front of plastics. But bioplastics is dividable or can be separated into two interrelated but totally disconnected terms. And that is bio-based plastic and this end of life, biodegradable, compostable plastics. And this is the fundamental mistake we make. Bio-based is simply answering the question, where did that carbon, remember we talked that all plastics are carbon-containing polymers, where does that carbon originate from? Did it come from plants or did it come from petroleum feedstocks? That is all. And is there a value or not a value? I think the last time we debated that with Shivram at some meeting. But that is there. But at least we need to know what we are debating. If we don't know what we are debating on, then there's nothing to debate about. So, bio-based plastics, which represents now a big driver in the US for procuring of products. EU also is correct. The bioeconomy, all those words come because there is and I will talk about this, there seems to be a value proposition that bio-based plastic can contribute, right? But it is simply talking about where the carbon came from. On the other side, you have biodegradable. In my opinion, this is the most used and most abused term. And originally I used to get very upset about it, but then like I was telling Ashish, maybe that's what got me invited to so many lectures, because they always wanted somebody who wanted to hear how this is so stupid or why are you using it. So I thank some of those people saying, I should really thank you because you got me invitations all over the world to talk about biodegradable. And it's not complicated, and hopefully we are going to address it, but we still talk about it, right? So I want you to understand, biodegradable, and I've refined it much so, has nothing to do with biodegradable polymers used in the body. When we first started this, even in the earlier meetings, we would have the biomedical people join with this environmental people and argue about what biodegradable is, which was, in retrospective, absolutely useless. The body is a system where if you use biodegradable, we say, oh, it biodegrades. But when it biodegrades, all you're doing is excreting the remains of that polymer from your body. And then it is fine, as long as it doesn't have any toxic reactions, so on and so forth. But biodegradable in the environment, there is nothing to excrete it out. So either you completely remove it, or ensure that it is completely removed, or you're going to leave something which may have consequences. And that is what we need to understand, that biodegradability cannot be partial. I use this, and there are ladies, so in the US I would not be making this statement, but you're either pregnant or you're not pregnant. You can't be quarter pregnant and half pregnant. That's what biodegradability in the environment means. When you say something is biodegradable in the environment, it means that all of that material is removed via microbial metabolism and nothing remains. No toxics, no intermediates, no nothing. Now you show me that, then we can talk about biodegradability. So the first part is very nice. Can polymer break down? Oh, we have umpteen tools, right? You can show carbonyl index, you can show biofilm formation, you can show molecular weight loss, you can show viscosity, and every paper talks about things like that. But that's not going to take it away from the environment. What you need to prove is, do the microbes present in that environment actually utilize that carbon as food through microbial metabolism and remove it. And so in these ensuing years, we have developed standards that allow us to answer this question, can microbes completely remove it or not, and what is the gold standard, the metrics by which we measure it. At that time, Shivram, we never had anything like that. We were just talking about it, but we never did have that. So here is another complicating factor in that. In the bio-based area, we always talk about this, natural versus synthetic. And today the European Union defines a natural polymer as something which nature makes in the environment. So cellulose is a natural polymer, lignin is a natural polymer. PHA, polyhydroxyalkanoates, made by microbes, is not a natural because you feed the bugs other intermediates which then makes a polymer. Then it's not. Like PLA is not a natural polymer. It is a fermentable bio-based polymer. It's not a natural polymer. And as Shivram pointed out, the politics of it is companies which make PHA want to make sure that it is classified as natural so they don't have to do anything about it. But then there are people like me who write all these long letters saying that this cannot be called natural, and I get into trouble with them on that. But I wanted to point it out to you because we still have that tendency when we work with starch or cellulose. You say we are working with a natural polymer, but then you acetylate it, you do all sorts of chemical modifications. There is no more natural polymer left there. So be careful on that term. And here is the key take-home message. If you don't listen to anything of what I say later, this is the key. You cannot talk about biodegradability in the abstract. You have to talk about biodegradability in what environment you're talking about. So, biodegradability in industrial composting. You'll see the lot of this thing. This is what we call compostable plastics. When we coined that phrase compostable plastics, everybody started selling and saying, oh, we are not compostable plastic, we are biodegradable plastics. Why? Because they could not meet the standards set on this compostable plastics. But what are we saying in industrial composting, as I'll show you? It is simply saying, can microbes, the second part, completely utilize your polymer carbon and remove it from the environment and not get involved with the other processes there? And what is the standard methods you will do or test to do that? Okay? Now, therefore, if you talk about other environments like ocean or land, you see that X there. I am a big proponent to say that you cannot claim marine biodegradable. Okay, I am one of those very sort of outliers who keep saying that, but every second day there is a product in the market saying we are marine biodegradable. Right? And why is the oceans is not your trash ground, it's not your dumping ground. So designing for biodegradability in the ocean environment is absolutely wrong. Remember, my title was Redesign Polymers. So you are all polymer engineers and scientists. Today you just make polymers and you find an application, you're done with it. The next generation cannot do that way. You have to design for an end of life. And you need to decide what that end of life is and how it is going to enter that end of life and what happens to it at the end of life. Do you see what I'm driving to? You don't do that. Maybe you do, I doubt it. I've not seen that. So tell me that you're designing for it. So then when we talk about biodegradable in soil, we are designing a polymer molecule that can be used in agricultural mulch film applications that will have the performance metrics of what is required in that mulch film application. But at the end of the cycle of using it and plowing it into the ground, a 2-year cycle, all of that carbon is removed from the environment. And so the state of California has a law which requires you to use, or which allows you to use biodegradable mulch film, and it is called biodegradable mulch film. The state of California also tells you that if you use the word biodegradable for marketing purposes, we will take you to court and fine you. So companies like Amazon, Walmart paid millions of dollars. Of course, that helped fund the CAW, the Californians Against Waste, and they could do all these things. Point is, when you talk about biodegradability, and this is the new thought process which I have now entered into, and I'm asking you to think about it, you need to previously we used to say talk about biodegradability in the context of the environment in which it is going. Now I'm saying talk about biodegradability in the context of the application you're talking about, and prove to me that there is value in that biodegradability and what happens at the end of life of biodegradability. Now we are on the right track. So you can't make just biodegradable polymers, you got to make it with a particular application in mind, and that application must be time sensitive enough to leverage that biodegradability, and that's what I'm trying to tell you. So when you talk about soil, that's for agriculture. Oceans, we use a lot of plastic products in the ocean, fishing nets, lobster pots, everything. Now, think for a minute, if you made it so biodegradable that the first time you went fishing, the next time it disappeared, that's going to be of no value. So you're going to design a polymer molecule that's going to last as long as it can. But at the inadvertent breakdown and loss into the ocean environment, how long will it last? That it doesn't last or persist and accumulate, that within 3 years, 5 years, 7 years, it's going to be completely removed from the environment. That is not a concept people are now still willing to accept. We are, in fact, if I have time, I'll show you the data on this. We are writing the standard for that. We are saying that you can call a product marine biodegradable only for products that will be used in the ocean environment. It is not to help you with the littering and it is going, the mismanaged waste which Shivram talked about. It's not to solve that. It is to solve a real problem of lobster pots, of things which are used, which could be lost. Then you want to say how long will it last and that it will not persist but will eventually biodegrade. But in that time period it will have impact. So don't ever forget that. And so what is the impact? What would be that 5-year impact we need to calculate? So my message here is straightforward. Composting and compostable plastics has a very definitive requirement. All other biodegradability terms are defined with respect to the application because there is a need for it. If you talk about polyethylene film for agriculture, they do break down, they fragment, then it goes into the soil, it is carried away, and it will persist. And you have no way of removing it. Whereas a truly biodegradable, which you have tested and shown that it won't last more than X years or whatever it is, you can use it. It is not a solution, but it is an acceptable risk and alternative for what we are doing today. That's what you need. And we need to be transparent in our messaging. We don't do that. We say it's biodegradable, period. For example, okay, I'll come to that later. I can send the whole lecture on this itself. So caution, bio-based does not equal to being biodegradable. Compostable and biodegradable compostable does not equate to being bio-based. I put this slide up with a reason, right? And I put it up because this is what the Intergovernmental Panel on Climate Change, so this is not my figure, this is their figure. I wanted to understand this carbon management, what is happening. And you notice that nature cycles carbon between 3 environmental compartments. Remember, first law of thermodynamics, you cannot destroy carbon and you cannot create carbon. So you can only distribute it. And so when you say that, oh, I'm going to remove carbon or I'm going to bury it or do something, you can't do that. You're just putting it in a different environment. And the question you have to ask is that good or bad? So if you look to nature, it's an amazing number. Even I am surprised by it. 730 gigatons in the atmosphere, carbon, 38,000 gigatons in the ocean. But the flux between atmosphere and ocean is balanced, 88, 90. If you look at vegetation and soil, 2,000 gigatons of carbon in the soil, but the flux is 119, 120. If you look at even agriculture, it is 1.7 to 1.9. So if you follow this concept of how nature cycles carbon and you can integrate your design with an end of life that can accommodate this cycle, then you're on the right track. But if you're using fossil feedstock, I think, which is nothing but also natural because this is carbon in soil, vegetation which has over millions of years given you a reduced hydrocarbon feedstock. We are using that and putting up 6.3 gigatons of carbon into the environment. Very simple. If you put the amount of this into the environment at the same rate at which you're forming this, then you're in balance and there's no problem. But that's not happening, and that is the problem. So when we say we want to switch to bio-based, at least the concept is, I want to be a part of this biological cycle. That the rate at which I fix it equals the rate at which I liberate it, and I'm in balance in terms of carbon utilization, and that's where the bio-based concept comes into play. All right. So, what is bio-based? You know, this is high school biology, all right? Carbon is inorganic carbon in the environment. Photosynthesis, you get this new carbon. Millions of years, you form the fossil carbon, and you can make a product. Now, here is a value proposition. We have taught how to calculate, and we have developed standards around it. If you make 1 kg of product from oops, what did I do? If you make 1 kg of product, okay, if you make 1 kg of product from plant biomass, you are taking carbon and embodying it into your polymer. Whereas if you take fossil carbon and making that 1 kg of product, you don't get the credit because that carbon has been fixed over millions of years. So it's a rate issue, not a total mass issue. Right? So the rate at which carbon is fixed into plant biomass equals the rate at which I put it into product. Now if I recycle and continue it and then put it back into that biological carbon cycle, I'm carbon neutral. It's an approach to that cycle. Whereas if I use fossil feedstock, or I reduce the use of fossil feedstock such that the rate at which I use it equals the rate at which it is being fixed, then also I'm okay. So it's a rate issue and not whether an absolute issue is what I wanted to talk to you about. So this was one of our best contributions. We wanted to say, how do you determine there is bio-based carbon in it? And it was not rocket science. The anthropology people, the tree people have been doing this. The carbon has 3 isotopic ratios, right? And you have radioactive carbon. The amazing thing is there is 1 radioactive carbon for 1 trillion carbon atoms. And analytically you would say that's an impossible. How are you going to detect that? But today accelerator mass spectrometry can detect that and give you an plus or minus 3% value of what is the percent bio-based carbon in your product. And that is what the basis of this is, right? So, very simple. When the system is in living, including our body, the radioactive carbon is in equilibrium and it is still radioactive. Minute the living system dies, the radioactive carbon starts to decay. And for us it's very simple, right? Half-life of radioactive carbon is 5,730 years. Fossil carbon has been formed over millions of years. So, bio-based carbon or plant biomass carbon, even 100 years old, would have almost the same radioactivity associated with it. It's only a 1% decay. Whereas fossil carbon has 0 radioactivity. And this is the basic simple test which is used to determine bio-based carbon content and the percent bio-based carbon, right? If we didn't have this, we would have lots of people cheating the system and saying, oh, this is natural, it is bio-based, but this is what it is. And I just wanted to share that with you. Okay. Why bio-based? And here is the reason. Of course, I explained to you why it's a reduced carbon footprint. But 2 other things I'll point out to you. Food security and create value for rural agrarian economy. If you give the farmer an additional value-added product to make, then he can, anytime there's an increase in the cost of making food, he distributes it over a larger number of products, and therefore it is economical for him. So it will support agrarian economies, and therefore bio-based products will be valuable. So organizations like yourself should be seeing what agricultural wastes or agricultural products can be economically transformed to an industrial product to replace fossil. And that really is the crux of the bio-based economy and the push by EU to pull bioproducts into the marketplace. Right? But this is also interesting. I bring this to you, that the way nature cycles carbon, photosynthesis not only fixes carbon but gives you oxygen. And how many of you have seen papers published which says that I can take CO2 from the environment and convert it directly to a polymer, propylene oxide. I can make polymers. And they say, give me money because am I not sequestering CO2 from the environment? And my submission is they're doing not valuable things. That's a wrong approach. Why? Nature is doing it for you. It's fixing carbon, giving oxygen, so why don't you work with the plant biomass? Why do you have to take CO2 and go directly to a polymer? Unless you want to get funded for a research which nobody else is doing. So I'm not a big fan of making propylene oxide or polymeric products directly from CO2. I would rather you give that value proposition to the farmer. Let him grow, let him give you something which you can use, both benefit, and that's why I believe that this value proposition is there. But, and this is where we fail, we make a bio-based product, but we don't worry about how to address the end of life. So Braskem makes bio-based polyethylene. And that bio-based polyethylene is used to make shopping bags. And of course, that shopping bag is polyethylene, so it persists in the environment, it accumulates. So what is the point of bio-based polyethylene then? Right? So unless you have an end of life associated with the beginning of life, you're not closing the loop around it. So to this group here, as polymer scientists, chemical engineers, you need to have a vision statement right at the top which says, my polymer design at the end of life will do what? Will it be recycled? Will it be biodegraded? And where? And how? That needs to be an integral part of any future developments in this area. And that is still not happening, and that is what I would appeal to you to do that. There's always greenwashing. And I bring this up because it's a very complex greenwashing here. There is the big industries like SABIC and BASF, ExxonMobil claim that they can add circular feedstocks or biomass feedstocks with fossil feedstock to make product A, B, and they say that they can attribute the bio-base to this product C using an approach they call mass balance approach. I have no idea what that means. Chemical engineering says if I put 25 kilograms here, I should get 25 kilograms there. So how do they take that fossil bio-based carbon, and how did that bio-based carbon figure out here? So they use a certification scheme called ISCC+. The mass balance approach makes it possible to track the amount of bio-based content in the value chain. It's a very complex situation. But my point when I presented this to BASF is, if you call this bio-based, I'm going to pull it in the market and test it using radiocarbon analysis. And if there is zero carbon, you know you're going to get trashed. So this is where the greenwashing comes from. There is clear value on using, if you have a refinery, a real RIL, for example, puts 20% bio-based feedstock. Obviously, you're reducing fossil feedstock, so there is a carbon footprint reduction. You certainly get. But that's all. You cannot translate that to say, I am making bio-based product. Unless you have a bio-based carbon in that product. I just thought you should be aware of that. Okay. I want to switch gears and tell you where the problem is. And nobody talks about it. It's kind of the sleeping giant here. On the top right-hand corner, you have global plastics production, 454 million metric tons, right? Do you know that 77% of that 454 million metric tons is coming from carbon-carbon backbone polymers? That it is free radical polymerization, that by simply changing that R group, you have created this beautiful portfolio of products, but it is still carbon-carbon backbone. And all the polyesters, polycarbonates, polyurethanes, they are an insignificant amount. So why are we wasting time? You know, Shivram asked the question, why are you not going after mismanaged waste? I'm asking the question, why are you worried about PET and polyurethane? What are you going to do about this? Where you'll have a bigger impact. The answer is nothing. I don't know what to do with it. And here is another staggering number. Packaging, which is non-durable, single-use or short life, 90% plus of that packaging is carbon-carbon backbone polymers. So where is the problem? It is the carbon-carbon backbone polymer which is non-biodegradable, persistent and accumulative. That is the problem. So why would you not innovate to change that? Why can't we not redesign the carbon-carbon backbone to give you products which can be easy to recycle, which can be easy to biodegrade, which can be easy to compost? And that is what I am submitting to you as a group, because you are the scientists and engineers who can make this happen. So, what am I saying? I am saying that radical polymerization technology should give way to condensation and ring opening polymerization technology, which will produce us a whole portfolio of products with ester backbones, with oxygen backbone structures, which is easy to recycle, easy to break down. That is where it should be. And that is why we need to move away from this carbon-carbon backbone structures. These are the ones which also form, so polyethylene will break down. In fact, there's a paper study which said sunlight breaks down polyethylene in the oceans. Yes, it does break it down. It simply degrades it. It fragments it. It gets smaller and smaller. But that polyethylene is not still removed. It is persistent. It is accumulated. There's no data which shows that that gets removed. So you have not really achieved anything. You have made it disappear from your eye. It's gone somewhere else. So that is what I wanted to plant the seed. So carbon-carbon backbones have to change. So this is the perennial problem. It's been time since I came here 25 years ago. They are saying that I can add a biological additive, a chemical additive, an enzyme, and I can magically break this carbon-carbon backbone to small molecules. It has been very hard for me to argue against it, but now I have found a beautiful way to articulate why this doesn't make sense. And here is the present thing there. So here's this question to you. You know about recycling. I mean, every one of you have studied it. For recycling, including pyrolysis, the amount of energy, 400 degrees Celsius in catalyst is needed to break that carbon-carbon backbone. Agreed? This is what you're doing today. So then my question is, if I add a magic additive, how does it break it down to small molecules at ambient temperatures? Why are we not questioning that? What is magical? What can an enzyme do to bring it? Because if you could do it, chemical engineering can take over processes. You can distill it, you can separate it, you can do all these wonderful things with it. But no, it doesn't work, and therefore it's a problem. So this was an easier way to convince chemical companies and chemical engineers and people who are a little bit removed from biology to say that you add an additive, the claim is it will biodegrade in a landfill. A landfill is ambient temperature. And for biology to take place, the molecule has to be small. That doesn't happen. And this is proved a lot, and it still continues to proliferate. And it happens in India, of all places. Because the US doesn't allow it, the UK doesn't allow it, the EU doesn't allow it, but they come here and start proliferating and marketing this very aggressively, unfortunately. I have this magic additive, it will make it disappear. So I just wanted you to point that out. So my submission to this group is think about design, engineering of changing the carbon-carbon backbone to ester backbones and come up with structural units around that ester backbone to give you the performance properties you need for that particular application. You don't need a paper, a plastic bag which is used to wrap candy which lasts for 1 month, 2 months, to last for 25 years. Unfortunately, the CPG companies have that requirement. They want a plastic which will package their candy 25 years. Okay, you can give it, but then it will never biodegrade. Why do they need that? Why can't they do it with 5 years or 6 years? So there has got to be a discourse and an engagement which says that you need to design ester backbones and you can come up with a whole portfolio of products. And by the way, PLA is also an ester backbone polymer. Okay, it is PLA, it has got CST, but it is also ester. And PHA is also an ester backbone polymer. And cellulose contains oxygen. So conceptually, putting oxygen in the backbone allows you to make it more recyclable, more biodegradable, compostable, but you have to test it out. So the design of polymers going downwards must include this. What is going to happen to your product at the end of life? And if you think polyethylene is still needed, how are you going to recover it and how are you going to recycle it? That needs to be an integral component of any money you spend on making new polymers for the applications we are talking about. That is what I wanted to make sure you catch up. Now, go into a little bit more detail. This is PET, terephthalic acid. It's got an ester linkage, but it is not biodegradable. It is not biodegradable in practical time. If you do certain things to it, you could make it. We have not studied it. If you melt it 270, 280, you dump it all into water right away, you quench it, it becomes all amorphous. Now you have enzymes which are capable of eating it. The enzymes don't go after the crystalline segments of it. So whether you want to break this polymer down biologically, chemically, hydrolytically, you must have the ester linkage. That's the messaging which I wanted to leave you with. But you still have to do the homework to see, does it really do what terms it will go as. This is the very clever way which Coca-Cola conveyed that bio-based plant bottle. Very easy, 10 carbons, 2 of the 10 was from bio-based. India Glycols gave them that, and they marketed this extensively. They called it bio-based. They can also calculate 1.42 kgs of CO2 removed for every kg of bio-MEG produced, all of that wonderful stuff. But then they had to recycle. So the elegance was that I make it bio-based, but I want to also collect it and recycle it. Then it was a complete story, and I just wanted to put that to you just to tell you that ester backbone is an essential ingredient whether you want to recycle or whether you want to biodegrade. And that carbon-carbon backbones are not. That's the past. We have to move away from the internal combustion engine to the EVs. Same concept here. We have to move away from carbon-carbon backbones to ester backbones. And that's not going to happen unless more of you people design, synthesize, make all these wonderful polyesters with great properties which industry can take and displace it. But if you continue to keep working on polyethylene and making it even more stronger, even more better, then we are in trouble on that. And that's the messaging which I wanted to give you with. So, this is a standard, I don't know, maybe Shivram you teach this in your class, but teach it with the way to say, this is what I do, use structures for polymerization or ring opening that you get a copolyester type structure. So this is a random copolyester, this is BASF's product called EcoFlex, where R group is terephthalic acid, the aromatic. So you have aromatic acid, adipic acid, aliphatic acid and a diol, and you mix and match so that you get sufficient melting point, which then allows you to process it. And it is still biodegradable and compostable. That's the beauty of this design. Right? They designed a polymer molecule which is an ester molecule where they dropped the terephthalic acid down to 20 mole%, filled it up with adipic acid, and used 1,4-butane diol. Why 1,4 not ethylene? They needed still a spacer flexibility to make films out of it. Very clever design. And that's what I'm saying. That's the capability you can deal with. So PBS, this is PBAT. You can use all sorts of acids. But here is what I want to leave you with. Polyester structures can be mechanically recycled, chemically recycled, and it can also be composted. Depending on how you structure the groups attached to that ester backbone, you can do any of the above. So you have an open end of life. It is bio-based, and now you have fulfilled all the requirements, and that's hopefully what I am recommending to you guys, right? But dimer acid, which is simply taking oil and dimerizing it, C18, and making a polyester out of it, this is totally not biodegradable, unfortunately. We thought we would come up with it. And the reason is pretty obvious. There's too many carbons. So it's not a simple, I can make whatever I want. You still have to do the biodegradability testing and do that. Okay. You can tell me when I have to stop. Like Shivram said, you give a podium to a professor, then he never stops. I wanted to, so just give me the 5 minute, 3 minute, I'll stop everyone. I wanted to share this with you because the question is always asked, even you asked me that, is it biodegradable? How do we know that? So, we did this study a long time ago. If you take this, this is the copolyester. It has got terephthalic acid, it has got adipic acid, it's got the butanediol structure. And we labeled this, we means Eastman Chemical did this work, labeled this aromatic carbon with a C14 label. And we wanted to take that film and see is it completely biodegradable or not. And we wanted to say the most recalcitrant carbon is the aromatic carbon, is that being biodegraded? And we labeled that C14, and this is the study. The green represents polymer carbon. And as you see, as the days in composting goes, that green translates to CO2. This is radioactive carbon, which means that aromatic carbon I'm talking about. Clear evidence that if you have the right polyester structure, even the aromatic carbon can be completely biodegraded, as shown here. And now they have done C13 labeling studies to show that. So here is some of the things which you can do to prove is that really breaking down, is it biodegradable or not. And this slide I do want to share with you because this is the most criticality of it. Biodegradability is not simply making it degrade. You are asking the question, is it removed from the environment? What? Sorry. Is it removed from the environment? That's what you're asking. So here is where the problem is. We can introduce linkages, we can introduce additives, we can do all sorts of things here. They will break it down to small fragments. Molecular weight loss, carbonyl index goes up, biofilm formation, everything but is it biodegradable? We never answer that. And what I am submitting to you is that you have to prove that these fragments are completely assimilated by the microbes as measured by the evolved CO2. In other words, think for a minute. You need to prove that the polymer carbon is completely converted to CO2 by microbial metabolism. Remember the key phrase, not by burning it, not by chemically changing it, by simple microbial metabolism. It doesn't matter what happens here. You need to prove this. And the requirement today is 90% plus of this polymer carbon has to go to CO2. That is what I want to leave you with. And this is the biology. In fact, you should read this biology. Microorganisms, why CO2, right? People ask the question, why do you use CO2? And I wanted to show you. So microorganisms utilize carbon by oxidizing it. It releases energy. That energy is harnessed in the ATP, ADP cycle. Just like you eat food and you'll harness it. So If you want to prove that microorganisms are utilizing a polymer carbon, you need to feed it to microbes, don't give it any other carbon food, and find out how much of that carbon is evolved as CO2. And if 90% plus is evolved as CO2, then and then only can you say that, yes, my product is completely biodegraded. And this is the requirement of the standards today. Very tough, very aggressive, and many products don't meet it. And that's why you see all these things. And it's not an easy process. Okay. So this is the test method you all should be aware of, which is to say that all I need is a flask. I don't give it any other carbon food except your test carbon. I give it oxygen, I give it nutrients. If the microorganism is really utilizing it, you should see CO2. So you plot percent carbon evolved as CO2 as a function of time. And if you can demonstrate this curve, 90% carbon conversion to CO2, then the standard says you can call your product biodegradable in soil or compostable. And it's very simple. If anybody comes to you and says, I got a biodegradable product, they need to show you this. And they'll give you all the reasons why this they cannot show. It's secret, it is confidential, I can't show you this. What is confidential about that? Right? Ask for this. And if you have it, I'm happy. Then you got every right to do it. This is, these are the standards which exist, and you can use that. Composting is a term which is used a lot, and I thought it would be useful for you to know what is composting, because this is my definition of composting. You won't find it anywhere else. Composting is simply a process to convert potentially pathogenic, disease-causing, odorous food and biodegradable organic waste to a stable product. It's an industrial process. It's a managed process. It's not a natural process. This is man-made, right? So this is composting. So you ask the question, and I recall Shivram always asked this question, why do I want to make it biodegradable? Why can't I, every plastics polymer person says that. Can I not recover it and burn it? I get more energy out of it. I can recycle it. I get better products out of it. I save carbon. I save this. I save that. And here is why compostable works. And this is why. 50% of the municipal solid waste stream is biodegradable organic waste. Do you know that? You just look around here, I can show you all the food waste dumped out. 50% is biodegradable paper organic food waste. That today in the US and all goes to a landfill, generates methane, which is a 25x global warming potential. If you do it like just dumping it, it also produces methane. Therefore, if you divert food and organic waste to managed industrial composting, then methane generation is eliminated. It's a managed process. Since these are all bio-based, they are carbon neutral, so you're not generating carbon CO2 into the environment. And therefore, if India or any of the countries, including the US, needs to manage carbon, reduce carbon emissions, they need to do this first. The amount of CO2 emission saving is significant. So for example, using a model, you can say that if you recover 1.84 million metric tons of organic waste through composting, you'll get a 1.74 million metric ton CO2 equivalent of GHG emissions reduction. That's dramatic. So if you took, I don't know what is the India's food waste generation, and if you said, I take 80% and compost it, you will meet the requirements of what you signed up for in all those treaties without doing anything, just doing compost. Because the question always is asked, she's asked me this morning, well, who's building industry? How do I do it? What do I do it? My answer is, how can you not do it? If you are serious about climate change, global warming, you have to do this. This is 50% plus of your MSW stream. And if you accept this, then all the packaging products associated with that food paper must be compostable. Otherwise, you are contaminating this with non-degradable persistent plastic. So this is the driver. Composting is not for plastics. We are not making compostable plastics as a solution of end of life. We are making compostable plastics to enable food, paper and biodegradable organic waste to be safely and efficaciously diverted to composting so that you manage the GHG emissions reduction. That, ladies and gentlemen, is the driver for compostable plastic. Nothing more, nothing less. There's nothing magical about it. And if you talk about recycling, I challenge you that, that recovering that thin sachet or that thin film from that food waste is going to take you more energy, more effort than simply composting it. So compostable plastics is certainly a viable solution which should be practiced, especially in countries like India, because you have a lot of food waste and you need to manage it better. And industrial composting, or IAD as you pointed out, is the way to go. And there are cities and places that are doing it. Remember then that the paper has to be compostable, the packaging has to be compostable, because the paper cannot be coated with polyethylene then. It has to be coated with PLA. So you see the opportunity and the volume of this business if you make that correctly. And you cannot recover that by recycling it. The last part then is you want to prevent leakage. That's why you need to do this test in ocean, in land, and in other things. And I can talk hours on how to do it, what to do it, but I worry that you are hungry, you're going to, there is always this finite element I can push you, like the students. Then they're looking up, they're looking down, they're looking at the stomach. So I'll stop here. I welcome questions. I'll make this available to you, and you can always send me why you don't agree or why you think this is right, why is wrong, and feel free to use it when people tell you all these wrong things. So thank you very much.
Thank you for this amazing talk. You really educated us about what should be the terminology to be used. Now, the floor is open for questions. I don't think I could manage to switch it on.
Yeah, lights would be good so I can see your faces.
Hello, sir. Hi.
Yeah.
My name is Aditya. I am a founder of Zero Plus Labs. We are a startup based out of Venture Center. We are a spin-off from CSIR-NCL. One of the questions that I had was, you have mentioned that one of the categories of biodegradable polymers you emphasized on was ester linkages, ester bonds, materials developed by them. Are there any other bond linkage, like why emphasis on just one linkage? And are there any other linkages that behave in the biodegradation domain in similar manner? Have you explored those?
I have not, but there are urethane linkages which are equally hydrolytically unstable. There are anhydride linkages. There are lots of other linkages. This is the easiest one, also because there are esterases and cutinases in the soil which are capable of breaking it. So it's just because it's the easiest one. And we have not even explored this, so that's why. But if you find other such linkages, yes, that is good. But what I will hope that you don't do is try to make carbon-carbon backbones biodegradable, because I don't know how old you are, you can get as old as me and you'll still not have progressed. And the proof is that 30 years ago, we had the same discussion in the same institute, and today we are still saying the same thing, polyethylene is biodegradable. And in 30 years, it has moved nowhere. It's still saying the same thing. So, yes, please, I'm not saying ester linkages, it's something we know. It has happened. And there's a lot of ester type linkages you can do. The other thing I wanted to stress is, I know that NCL started this lactic acid PLA which got mothballed, and I'm telling Ashish is that, but polyesters and processes and engineering of that should be bread and butter. I mean, bread and butter to this group here. And so you should be able to design all these things, test it, and find out and come up with new polymer molecule. That's all I'm saying.
I have a follow-up question.
Sure.
So PBAT, PBS, they have been well studied from past 15-20 years, which you have mentioned, like by BSF, by Mitsubishi, with the MCC, right?
Yeah.
Are there any other ideas that you would like to share with the group on which we can at least start exploring on?
Well, I would, so there is a typical tendency for everybody to go after making polyhydroxyalkanoids. It's very attractive, it's made by microbes, so it will be degrade, all of that thing. But I think the space where plant oils, they are lipids, which has got double bond, and you can ozonate it. You can create all sorts of azelaic acid and sebacic acid, all these diacids and diols. Nobody has explored it. Arkema takes India's castor oil and they ship it there to make that nylon 611. Yeah. Why are we not? Why are we not doing it here? And why can't you use it for some of the polyester? So I think the country is rich in these renewable resources, and it would in NCL way back when I was looking, I forget the name. You were big on CNSL liquids. Now there is a U.S. company which is using it, Cardolite. You may have heard of that name. They build the plant here.
They're here in India today.
Yeah. Oh, they are. They are very good friends of mine. So, and they have given me that epoxide. It's beautiful structures, right? You can use that to make polyesters. In fact, that's what they are also wanting to do. So, what I'm saying is, think outside the box. All you need is either a cyclic ring, strained ring, or two hydroxyls, or a hydroxyl and a carboxyl of the same backbone, and you're in business. That's what I'm saying. Yeah.
I'm Samik Chikalia. I have two questions. One is about, I think what he asked is, there was a lot of stress on using ester groups. I was thinking, are there alternatives? Are there better groups, for example, acetals and oxalates, which are much more pH sensitive, and if you use those polymers, they might be also degradable or biodegradable. That's first part. The second part is about biodegradability. If you think of converting everything, all the plastic, 400 million tons, into a CO2, is that not counterproductive? I mean, we are talking about reducing CO2 emissions, and at the same time, we are saying, okay, we will degrade all the plastic to CO2.
I love this question. It's always asked every time. The first point I will push back to you is, I never said make all the plastics biodegradable and compostable. If you remember, I showed you where. I said in packaging products used with food and paper and other products, make that biodegradable under composting conditions, right? Now, you say that I will recover it, I can save the world of CO2 and all that stuff which you just said. You know how much of that plastic has been recovered from that in the last till today? 2% to 0%. Are you saying to me that in the next 10 years we are going to go from 0 and 2 to 90%? The recovery is the problem. You're not going to be able to recover it from food. So my message is pretty straightforward. We use a lot of single-use, essential, necessary plastic polymers with a lot of food and paper and other things. And we cannot afford to throw this food, paper in the open dump or in landfill because they generate methane. So what do you do with it? You're going to do composting. The composters don't care if you make your plastic compostable or not. They are happy with food waste. In fact, in certain states in the US, they ban compostable plastics. They don't want anything. They just want food waste. But then how do you collect the food waste? So you go to your cafeteria, you got this bin, you throw all your food waste into that bin, then you have to clean the bin with water. Then you have the ick factor. Then there is these pathogens which could be formed. And in today's world, you wouldn't want to put your hand in there, would you? So you'll use a plastic, it protects you. So the gloves, the masks, the food packaging, all of these products are necessary, but they are not compatible with the end of life for that over there. That's why you make that compostable. So the argument is correct if you can recover the plastic, what you made, CO2. And the last point is if this was bio-based, that's where the concept of bio-based compostable plastics comes into play, then that you're putting CO2 is lost. It is carbon neutral. Nature does it. Nature grows trees, breaks it down, then sends it to CO2, fixes another tree and it grows. Why can't you do what nature does? So those are weak arguments. And whether you should use esters, that is your first question. I have learned that if you give too complicated a message, it never gets heard. So if I said acetals, anhydrides, you can do it, then nobody listens. If I bang it down and say esters, the message gets across. That's the only reason I do it. It's just my style, but both of you are right. Don't get hung up only on esters. There are other linkages which will do much better, give you better performance and give you biodegradability, like glycosidic linkages, amino acid, urethane type linkages. There's so many linkages which you can exploit, but we have not done the data. You have to do that. Don't just make it and then say it's biodegradable. I need to see that graph, carbon 90% conversion to CO2. That make sense to you?
Yeah.
Okay, good.
Thank you, sir. Very nice presentation. I am a student of Dr. B.D. Kulkarni, basically a chemical engineer, basically acidically neutral everyone. The thing is that very good that you talked about that biocomposting and we should use that biocompostable plastics. But the food material will be compost much faster than whatever be the carbon bond. Will it not then again affect the rate, because rates will be different? So how will it be afterwards?
You're right, and you are a BDK student, because I'm sure you would have asked me that same question. Is the rate? The rates has to be the same. When you do the food waste composting, and this is what I was telling Ashish, is there's so many chemical engineers. Today composting is like the steam engine type composting. You build a pad, you throw your stuff in it, something breaks, something doesn't break, you turn it around. You have a lot of labor, so you do it that way. Why can't we design a flow reactor? You are the ones who should come up with that design, right? Continuous flow of feed. I put food waste in with water. What is the right amount of water? And these products, like I'm talking about packaging, and they will all break down. We have already shown it. So you test yourself. But change the concept of composting from a old, 15th century, 16th century thing to maybe come up with a new name, right? Maybe we shouldn't say composting. But can you develop a process flow composter where you have a continuous feed? At what rate would you feed it? I mean, these are the questions you ask as process engineers, right? Why don't you do that? Then suddenly you'll see every hospital kitchen, every school campus can put this flow composter at the back end of it, and as you generate food for that hour or that day, they dump it in there, it goes through it. At the end of the product, you get a stable product which they can put on land or put it somewhere else to let it stabilize, and you continue to add more food, and you manage the process so that the rate of input equals the rate of output. That's what chemical engineers do. And unfortunately, BDK is not with us, but I'm sure he would have appreciated this concept. And so carry on that thing.
Only one quick question. The CO2 release from the STM biodegradability
Yeah.
test is a 180 days test, right?
Yeah.
It's a 6-month test. And this is a problem in India today. We have very few centers where biodegradability tests happen. It's a 6-month test, very few centers, and a lot of demand to do biodegradability tests. So the question that we keep getting asked is there a faster way to do it? Is there an accelerated biodegradability test? Is there anything like this? Is it
So-
a 1-month test?
So it takes 9 months to make a baby. You can't accelerate that. That's biology for you. But there is a miss. When you say 180 days, that's the maximum time, because then the microbes won't survive that. Typically, if you look at all these products we talked about, PBAT, PCL, PBS, PLA, it doesn't take more than 75 days before you see 90% carbon conversion. Remember, you're comparing with cellulose as the control. So 180 days is sort of the maximum set, but anything below is acceptable. And two, why shouldn't this is not a complicated test, right? All you're doing is, I showed you that you have a reactor, a glass jar, you put compost, you can take your soil, pump air in, you got all these wonderful chemical engineers, they can put a manifold, they can pump 10 such things, collect the CO2 in tubes of NaOH, titrate it or use auto titrator or gas analysis. You'll know whether it's biodegrading or not. You don't have to wait 165 days to know that that line is just plateauing. This is not every lab, this is a rather complex, not complex, a charge statement. Every lab, like an NCL, should not be sending this outside. They need to have this testing done here. You should have an incubator room, put a manifold. I mean, you can take the design from us, we set it up. Automate the whole process. You have a sensor which detects CO2. You can have 35 flasks going. You can do all of that.
The commercial rigs that are sold today are crazily expensive, and I've always wondered why. They have some electrolytic cells to make high oxygen. It's ridiculous. And I keep asking, why should it be so expensive? It doesn't look.
It's the old supply and demand theory, right? The other thing I'll tell you, those ox meters, I wouldn't trust it for a 10-foot pole. Remember, they do measure carbon too, but they measure oxygen. They do measure oxygen, oxygen consumption. The problem is there are other species in that biology which also consume oxygen. So your oxygen data is always higher than carbon data. That's why if you notice all the ASTM ISO standards, they always talk about carbon standards, not. Ashish, this is not complicated. I do it in my lab. I have, there is a test called ISO 14852. It's aqueous. I go to the wastewater treatment plant, collect the inoculum, right, the waste string, extract with water, and put it in my aqueous water jar, put my polymer product, and measure the CO2 coming out in a tube. And because they are students, I want them to work in those fancy, automated collection. They have to titrate it. I mean, you don't have to be that cruel. You can buy some sensors and some automation, and you have the people to do it. I think that it's if what I've said to you makes sense to you. In order to incorporate this, you must have your own biodegradability testing system. If not for anything else, are there when you make these new polymers, even polyethylene, if you want to say polyethylene is biodegradable, which we have been saying for 20 years, put it and show the data.
It's good business today. One test costs 3 lakh rupees.
Really?
It's ridiculous.
It's ridiculous.
It's
And,
ridiculous.
and
Absolutely
I have been saying this. It is ridiculous, and not only that, much of that data is unreliable.
So there is a lab. I shouldn't probably take name. There is a lab in India.
I know that.
You don't have 2 labs. I can't trust that data. They tell you whatever you want to know. If you say I want it to be 90% biodegradable in 80 days, they'll draw the line and give it to you. And I tell you, I proved this. So I shouldn't make this so public, but in California they prosecute all these people, and so I'm very the attorney generals in the states of California are very friendly. I'll get this note. What do you think of this? And then I will see it. They say, look, they say 90% carbon conversion. And I plot that data on Excel. I don't do it, my students do it. And say to them, look, this is biodegrading faster than food waste. Because nobody thought of the rate. You know, you can plot the rate. You know, that's what chemical engineering students are very good at. And I send it to them, and they go and catch them and say, you're cheating. Look, you're doing this. Then they go away. And then they go somewhere else and do the same thing. So, but I think, I agree. I think really, Ashish, if there's something which, if we agree that this compostable, and I promise you it's going to grow more and more, if this is to get legitimacy and it cannot be just SIPET in, to do that. That thing was set up by me, by the way. That whole procurement of all those things. It's not expensive. It's not the kind of costs you guys are talking about. So all the preliminary work you can do. For final certification, you send it to SIPET. That's the way it should work. So, and you are a national lab, and you are a chemical lab, and this should be like very important for you to do.
But then, you know, what's the point of certifying compostability when you have still not specified the end environment, you know? So what's the meaning? Ultimately, it goes in landfill. You know?
That is the challenge.
Because compostability certification has got no meaning, and you know, when you don't have a composting environment where you can send that waste, you know. So you can right now here, you go to Starbucks, you know, you get everything, you know, you get compostable, what they call compostable coffee cup, you get compostable coffee lid, but where do you throw them? You throw them in the same
That is an error.
Yeah.
But this is what is very,
So
I am
now I
very,
think they are coming now. The question is, should we have another bin for compostable items? Now with that bin, now where will it go? You know, we don't know.
no, I would not recommend that. So I'm a big fan of, if you let the public decide which bin it will go into, it will be totally contaminated. That's not the way to go. So in the US, for example, what we say, these are, you can look them up, Green Sports Alliance. So if there's a sports stadium or a campus, since you control the concessions, any product sold in that campus has to be compostable. Or you must be a bottle which is recyclable. You can't sell anything else. Now there's no contamination. Now you compost it. The other interesting thing which I am very pleased, which only India has done, which is remarkable, the EPR guidelines which has come out now says you can't simply say it is recyclable. You have to show, I think there is in 5 years, 30% has been actually recycled. Well, they are also saying the same for composting. You can't simply say compostable. You need to show 30% will be composted. I'm a big fan of it. I'm the one who pushed it also. Why should the compostables get an exemption? No, I'm compostable, so I don't have to do anything. They also have to prove it. So I think the EPR rules will push that.
So once that environment comes, that certification
Becomes
right
important.
Now you see products sold in the marketplace with the compostability, whether the data is right or wrong is the second question, but at least they have the certification. But the question basically is, you know, there is no end of life guidelines. So like now the US has created this end of life guidelines, you know,
yes.
on the packaging itself. Okay, so you know that it has to go to that particular
End of life. Yeah.
but today, without that, it still all ends up anywhere in the landfill. So, you know, so it makes there's no
Yeah.
value proposition for, you know, in that sense.
Go ahead.
So, yeah.
Yes.
Hi. Thanks for this very thought-provoking and label-challenging talk. I have a question that is kind of connected to what Samir earlier asked about the CO2 emissions from the compostable process, the composting process. And your comment earlier about allowing nature to do its thing rather than capturing carbon through different processes. So what are your thoughts on using algal biomass and cyanobacteria and all these other microbes to make value-added products using CO2 and sunlight?
Amazing people, yes. The issue, so there are two separate things. Yes, cyanobacteria actually creates inorganic carbon too and that's a very elegant chemistry. Algal blooms, they grow everywhere. We waste it. Can you use it to make, take the lipids and create the monomers? The challenge, you can look this literature up. If you go to the NREL, National Renewable Energy Laboratory, which did a lot of these algal studies, the problem with algae is that if you grow it in a pond, the sunlight comes only till the top part of it. Then whatever, it doesn't go below that. And then if you grow it in a pond, you have more water to, so you challenge your chemical engineers. How are they going to squeeze all that water out at cost to allow you to extract the algal biomass to do whatever you want with it? I think the ability to take algal biomass and do wonderful things with it, no question. Even we did it, we published it. That's academic, you know. We can publish another 10 papers, but if that has to be really commercially viable, the answer is not in the technology. The answer is in the how do you extract algal biomass efficiently from the system. You know, they use photobioreactors. You would have seen this in the University of Arizona and all. So you have all these tubes, and they put a tube light inside of those tubes, you know, a light source. The amount of energy needed to do that is greater than the energy. So suddenly energy costs become higher. It's the same reason why electrolysis of water. If you put more energy to break water into hydrogen and oxygen, and the energy you get out of it is less, then what is the value? Not that it's not doable, but that's the challenges which you need to work out and not focus only on the product application or the product utilization part of it. The challenge is in this, how do you get algal biomass very efficiently? And I think it's a very good project because algal ponds also clean your water. So if you do an anaerobic digestion, which I think in Pune you said somebody's doing it, what people don't tell you is that anaerobic digestion is a very water intensive process. The loadings are only 10% solids or maybe 15%. 75% is water. So what do you do with that water? You have to recover it. Otherwise, you know, you're creating another problem. So what they do is you take the water and you grow algae. So you purify the water, you recirculate the water. Now you have an algae which you can use. So they are complex systems which needs integration, which is okay, which is in your bailiwick to do. You have the right people to do it, but very good thought and people are pursuing it. One last comment to you, if I may. When people started this, they found that if they grew algae and pelletized it, they can get more money by giving it as fish food than doing whatever you said. That is the biggest business in the US now, fish food from algae.
Yeah.
And they all started very nobly. Sorry.
So I just have one question on this compostability test, and we talked about the rates. Do they provide any guidance on the microbial load which should be there while doing this kind of test?
So they do. So if the ratio of how much of compost you put to the amount of carbon you take, it's there. That's one. So yes, that is there. But you raise another interesting question, which is kind of kinetics. We model this kinetics, and as you know, the amount of microbes is disproportionately larger than your feed. So we can model it as a pseudo first order, and therefore we can estimate. So if you do a pseudo first order kinetic, you can generate a global kinetic equation using the Arrhenius, incorporating the Arrhenius equation in that rate law. I think you guys know that better. Then you can estimate time for 90% removal, which is the ASTM standard we are writing. You see what I'm saying? So I would recommend that. That's how you would get the rates and all, by looking at by changing temperature. So for example, in the oceans, if the temperature, we are saying you do it at 3 different temperatures, 40, 30 and 10. Okay, 3 temperatures. So 10 degree biodegradation is going to be much slower than 40 degrees, right? But if I can document that this does follow first order kinetics, which you will prove either statistically or by integration and doing that, if it is first order, then you apply the first order rate law, use a reparameterized Arrhenius equation, and you can then estimate it time for 90% removal. Right? You can do that. It will give you, and you don't say it as absolute, you do cellulose with it. So you are comparing it relative to cellulose, which is an acceptable, fully biodegradable polymer. So you would say for 90% biodegradation in the ocean at 10 degrees, it takes 5 to 7 years. Cellulose takes 2 to 3 years. Okay, fair statement, scientifically backed, but polyethylenes take 100 plus years. It is in that, I don't know whether your people will get upset, but I'll just, oh, my computer is gone. So
No,
I'll just show you one last slide on that, because what the question you asked is, you will be familiar with this equation. So if you look at this, we simply use the first order kinetics, plugged it into a reparameterized Arrhenius equation into a global model, and then said what happens to PHBV at 10 degrees cellulose and LDPE. And you see where LDPE is. And you see this is, so what are we saying? That these products are not persistent, not accumulative. But you can't simply state it. You have to provide data like this. I'm just trying to convince him that I do know some kinetics and chemical engineering. Just kidding, just kidding.
Yeah. I
Yeah,
guess we can still continue another 1 hour or even more, but since there's lunch waiting, we should call this, like that was the last question. Let's thank again Professor Ramani for this amazing talk, which also had science. So, as a token of appreciation, we would like to give you some memento, and I'll request Ashish to present.
I'm going to come down, or you're going to come up? Okay. Oh, very nice. Oh, this way. Okay. Oh, let's go on from that.
Yeah, I think we can switch this on.
This is painting by one of my colleagues.
Oh, beautiful. I'm now a adjunct alumni of NCL.
Yes, you are.
And one more thing. Oh. Oh my God.
I know you will.
I don't
Difficulty carrying it.
but I'll give it to Shivram. So every time I come, I can, or one of the ladies can take that. So yeah, let's.
This is based out of PP COVID kits recycling.
Oh, this plant kit. Yeah. Oh, cool. Thank you. Very nice.
Instead of incinerating it, we put it back into one more life before it. We don't know where it will
Where it will go. Very nice. You know what? You should. I'll sign here, and you put it on your in your office.
All right.
I'll put a date and sign.
That would be nice.
Even if I wanted to take it, the
I know.
customs will not. There will be no other reason except to stop.
They have to say you are stealing the biodiversity.
I'll let you close it, right?
Yeah. So we have now come to the end of this B.D. Kulkarni Endowment lecture. I would.
One small comment. Those of you who are scientists who are deeply interested, please look at Plastics Technology, January 9, 2023. There's a beautiful discussion between him and the editor on compostability. It's a very, very interesting. Please read that. January 9, 2023, Plastics Technology.
Yeah.
What is compostability? So but there's a lot of discussion on compostability, so I think there's a huge gray area of thinking. So I think yes, it's a blog written, based on, he said we had a couple of hours of discussion with him, so.
He wouldn't believe what I said, so we had to go through this back and forth.
I read that.
And then
Very,
he
very
said,
nice.
okay, I will write it. And then he said, I've changed my mind. And hopefully he said, you have changed it. But I have not changed anything, but okay.
It tells you the complexity of, the nomenclature.
Okay, so first of all, Ashish, thank you for starting this endowment lecture series. We all agree that BDK was an amazing scientist and an amazing person, and he deserves this kind of a lecture series in his name. And I guess all of you know why I asked Dr. Shivram to introduce the speaker, because he said everything what is not written in that. I would have read out whatever is written in that in his bio sketch. So you got much more insight about Professor Ramani than I would have told you. And now the formal vote of thanks to all the people who helped this event to be successful. Mr. Sunil Patel, Dr. Nikhilesh Yadav, Ms. Sonali, Shri Ganesh Mane, Mr. Jagtap, Shri Avinash Teotali, and Shri Sanjay Askar, Mr. Javed, Mr. Mane, Mr. Yogesh Mahajan and his team, Mr. Mishra, Mrs. Asha Shinde, and Mr. Deepak Jori, and Dr. Swati Chadda. Thank you all. Thank you all for being present for this talk.